Hello, everyone. Thank you to join this session. I'm Enzo, and here is Bennett. So here we want to present how to enhance the QEMU RVV implementation performance. So why we need to enhance QEMU performance here? And I believe some people here may use QEMU in a CI/CD pipeline to verify your software. And when we don't have enough develop board or enough FPGA, and if we write a software with RVV support, we may want to verify it with different RVV combination, like we want to test with a different VLAN or different mask or tail agnostic. So QEMU could be a suitable choice because user can just modify the QEMU CPU options to create a corresponding environment to test different RVV combination. But however, when the software with more and more RVV instruction in it, then we observe that there's a slowdown in its performance. And actually, there are several discussion and issue track that many people report that QEMU, there are more RVV instruction and QEMU runs slower. And it could be very painful because we need to spend more time to get the verification result. For example, if we compile the SPEC CPU benchmark with the vector optimization, then it could take maybe a whole day to get the result running on the QEMU. And before we try to find the hotspot functions and optimize it, we need to define what the target benchmark here. And the first one is the simple test bench or the test case that we can find in the QEMU mailing list or the issue track that developer provide a test case on it. And the other one is about open software with RVV support. And because most of the RVV performance issue that in the mailing list or issue track, they are just focused on the RVV load store instructions. So here we choose the glibc memory copy function as one of the target benchmark here. And the last one is the CPU benchmark. We choose the SPEC CPU 2017 integer benchmark as the target benchmark. So here is the, Here's a table to show, that we reproduce the simple test case and to double check the performance number. And we can see that in the table in the left-hand side is one of the simple test case that we can find in the QEMU user track in the GitLab. And we can see the RVV version will slower than the scalar one. And the right-hand side is a chart that we use the glibc memory copy test bench. And in this chart, we can see that actually in this chart is higher means slower. So we can see when the memory copy implemented by the RVV version, it will slower than the scalar one. So right now we choose the memory copy as a target benchmark to find out the hotspot functions. On the left-hand side is the memory copy implementation in the RVV instructions that we can find in the Bionics glibc library or in the glibc upstream path set. And the right-hand side that we use perf tool to do the sampling-based profile to profile the workload of the memory copy test bench here. And we can see the top 10 hotspot function will spend more than 80% of time. So let's see what this hotspot function. And here on the left-hand side is the top one hotspot function. Actually, this function is the main function of the vector unit stride load store help function that we can see in the previous slide. There's a VLEA or VSA instructions. And this function will simulate the behavior of vector unit stride load store. You can see there's a for loop. They'll iterate all the elements in the vector register and call the LDSD element function. And actually, you can see on the right-hand side the hotspot function that label with the blue label. Actually, this all hotspot function is called by the LDSD element function. So let's see. And this function may spend more than 40% of time. Let's see what this function do. And actually, this function is a function point that point to a QEMU load store API. And QEMU load store API will try to do so many things. You can see the code stack here. it will try to handle the QEMU plugin interface to make sure the QEMU plugin can catch every load store operation. And in the same time, you also need to handle the address translation. In the QEMU, between the different mode, maybe a system mode or user mode, you need to handle a different address translation flow. In the system mode, you need to simulate the software TOB and do the page table work. And in the meantime, you also need to check the page permission. And even more, if we enable the PMP, you also need to check the PMP permission here. So that's why if we iterate all the elements in the lat loop and do so many things, that's why it's slow. Okay. Okay, here, so how do we reduce the overhead from the QEMU load store API here? And actually, QEMU has support various guest architecture, and every guest architecture may have their vector instructions. And here, the on-SVE load store instruction, actually, it has optimization to reduce the overhead from the QEMU load store API. So the idea is that in this optimization, you will check, you can get all the elements, active elements that in the beginning. So that means you can know the start address and end address of the load store element. And you just try to prop the corresponding pages to cover this scope at the beginning. And so what the benefit if we prop the page at the beginning? The benefit, one of the benefits is that if we can prop the page at the beginning successfully, that means QEMU can get the address translation result of the target page first. So we can, that all elements in the same page, they can reuse this translation result to do the direct access into the host memory without do the address translation every time in every element in the load store flow. And another benefit is that when we can prop the page successfully, then in the same page, every element, that means you will prop successfully, that can pass the page permission check, and all the elements in the same page can just, since that it also could pass the page permission check. So we don't need to do the page permission check every time for the element in the same page. So that's why it can reduce the QEMU load store API overhead, because you can just make sure if we can prop the page successfully, then all the elements in the same page can pass all that things. And so the question is how can we apply this patch on the RVV, and what challenges we will meet? And there are several differences between the on-SVE load store instruction and the RVV load store instructions. One of the differences is that the resolvability. In the RISC-V vector spec, it mentioned that implementation need to make sure the vstar CSR need to contain the correct element index when there's a trap, to make sure when we finish the instruction handler back to the vector instructions, it can just restart from the element from the index store in the vstar CSR element. So when we apply this optimization on the RISC-V RVV load store instructions, the first thing that we cannot, like on SVE, to prop all the pages at the beginning to fix all the page fault at the beginning, because that means we can get the correct vstar CSR. So what we do here, the idea is that we prop the page at a time. For example, we just prop the page corresponding to the first element, then to see if the prop successfully, we can, like on SVE, to fast access to reuse the translation result to pass the page permission check for all elements in the same page. Then after that, we will check the next page, then iterate all the page at the end. This can make sure if there's a mirror trap, then we can just make sure the vstar CSR can get correct number, because we can just revert back to the slow way that uses the QEMU load store API, like original implementation. And there's another difference that may make the optimization different. because when we enable the PMP, and the PMP, because the PMP's checking granularity may be smaller, granularity may be 4 bytes, which is smaller than the page size. So when we pop fail that caused by the PMP permission check, then in this implementation, we may lose some optimization opportunity because we will just force all elements in that pad fail page to go through the QEMU local API way. But as a trade-off, we want to make things, implementation simpler, and in the meanwhile to make sure the restartability is correct. So that's another trade-off that we made in this optimization. And this optimization is on the reviewing, and we hope it can be approved before the QEMU next release. And in the meanwhile, we also do other optimization list here. And some of this is approved and already approved by the QEMU opportunity and emerged back to QEMU. And some of them are still reviewing. And here, after that, we can show the performance result. And here is the experience settings of the performance result of following benchmarks. And it shows the host machine and the compiler version here. First, we want to show is the glibc memory copy test bench here. And here's the two charts. One of it is for the QEMU user mode, another one is QEMU system mode. And in this chart, slow means faster. We can see the red triangle. It means the QEMU after apply the patch, optimization patch. Both the QEMU system mode and user mode will be faster than the original QEMU RVV implementation. Even more, it can faster than the scalar version. And here's another test bench that we have mentioned that we can find in the QEMU Redis and issue track. After apply the optimization patch set, in the user mode, we can get 9 times faster, and in the system mode, it's 15 times faster, when the VLAN is 128. And here the SPEC CPU benchmark here. In this benchmark, we choose integer speed, and with the reference input, and VLAN is 128 in user mode. We can get average 22% performance improvement in the CPU spec benchmark here. And the last one is Android bootup. And with the original QEMU, we may need 20 minutes to boot up a Linux to the operating screen. And after apply the patch, we can just need to 10 minutes, almost 2 times faster to boot up a Linux with this optimization. And right now I mentioned that this patch is still reviewing, and in the meanwhile, we also try to optimize more RVV instructions. And because this patch set is focused on the unmasked unit stride load store, we also want to extend optimization to more different tail or mask orthogonaltic behavior. And the RISC-V project also tried to improve the RVV performance, and that Jeremy will introduce what the RP05 current state here.
Thank you, Max. So the RISE consortium has had a contract with Embecosm for the last few months to try and boost the amount of work done from RISC-V vector. There's also work being done by Alibaba as well. So the community is coming together to recognize this project. So we try not to duplicate each other's work. So our work has tried to build on top of what Max has done. And all this work so far has been through helper functions. And there's a bit of debate where for vector, usually you want to generate just direct operations in the target architecture. There's a bit of a debate whether for big complex vector instructions that always wins. And certainly one relatively quick approach, it's not that quick, is to try and speed up the helper functions that we're using at the moment to try and get better performance. And where Max has some phenomenal results. We've got other results that I've done where we've looked at the actual performance of individual instructions, and some of Max's performance gives you an 80-fold speed up in a load or a store instruction for big vectors and big data. We wanted to focus on actually making sure it also worked for small vectors and small data, so one VLAN 128, and perhaps where you're only copying 1632 bytes. Because that, as the statistics show from the glibc benchmark, are the common ones that you see in something like SPEC CPU. So one thing is not to try and do it bytes at a time because you've asked for a byte operation, but just always do 8 bytes at a time, okay? That reduces the number of loop iterations, and it works whatever your architecture is. But the other thing is, when we're doing these moving stuff around, rather than trying to sort of hand code the moves, we use the built-in memcpy function. And that means all x86 architectures, all ARM architectures, will have optimal use of their vector units to do built-in memcpy. So one of the criteria was to make sure that when we did vector operations, we used the vector operations on the actual machine running QEMU. And that's done with built-in memcpy. And I think Max actually now has that in his latest version of the patch, the use of memcpy. It's a simple trick to get the best out of the architecture. And we can look at we've done some other operations for data blocks that are larger, though, as I say, Max has already got that covered. So where do we go forward from this? There's two things. And so it's very easy in these talks just to give you hey, everything's perfect, everything's wonderful. But I want to talk about this slide because this is where it isn't wonderful, and we have to work together as a team. Because we've looked at Max's patch set, and he gets a speed up of 1.22x, and we thought, well, let's put all these extra changes. It's going to make the small mem copies and everything work really well, and you don't get a statistically significant improvement. In fact, we slow down Max's somewhere. And that's a bit head-scratching, because we look at individual instructions, it seems to be good. And the problem is, Max is running the same test suite as I am, and I get different figures. Okay? So actually, it turns out that measuring QEMU performance on big, complex software, which what the whole point of SPEC CPU is, turns out to be really hard. And even when you're working really close together, and we're using AMD Threadrippers, and he's using AMD cores, we're still working on this, because actually, you've got to have confidence that you're both doing the same thing. So we lay out our dirty washing and say, oh, well, we're still working together to try and work out why we both see a speed up, but we see different results and why that is. So we're continuing to work on that, and also to understand why, having made all these improvements, it hasn't made much more than Max got with his patch that's about to be merged. Okay? So where do we go from here? The first thing is to do it, the whole point of QEMU is you're supposed to generate the opcodes of the actual target architecture. And you do that internally via tiny code generation ops, or TCG ops, which then the back end will turn into x86 or ARM or whatever you're running on. Rather than what we're doing at the moment, which is where we actually just do a call out to like an emulation function, a helper function. So that's the next thing we do. And there is a slight question as to how much more that will give us, but hopefully that'll give us speed up. There are some other optimizations we haven't done. Fault only first vector load. So you don't if you're doing a whole vector load, you don't keep on checking for the fault. You do it once at the beginning, and if it's going to fault, you throw the exception. And looking at what we can do to boost strided and indexed vector loads. They're not actually terribly common in the, say, SPEC CPU 2017 code base, so we wouldn't necessarily see a huge performance. That's what we're doing under RISE as Embecosm. Embecosm is also doing our own work on that. One of the things we're observing is QEMU does not optimally handle VSET VLI. And we think from looking at the profiling data, like Max showed you earlier, that there is actual opportunity to do that. But that's not in the scope of the RISE project, but we do work on QEMU outside RISE as well. So that's where we're going. We work together, we look forward, we try and build on, we'll pick up the Alibaba work and develop on that. And the goal is to actually try and get SPEC CPU for RISC-V vector to go as fast as it reasonably can. It's not going to be faster than scalar because they're more complex operations, but it certainly shouldn't be hundreds or thousands of times slower either. Okay. So, questions? Someone's running around with a microphone, I think. Yeah, it's
who is going to ask? Any questions, folks? We have time. Any questions? No questions? No?
Okay.
Okay, I think that's it. Thank you very much, folks.
Okay, thank you all very much. Well done, Max. Good stuff.